Hey everybody, in this video we're going to talk about the basic fan laws and the calculations related to those fan laws. These laws are also referred to as the affinity laws. You might run into that terminology as you get started in your career. These fan laws, the ones that we're going to talk about, there are other fan laws that we're not going to discuss. That's why I'm referring to these as the basic fan laws. These are the laws that show up on certification exams. But the ones we're going to discuss look at the relationship between the RPMs of the fan, or the revolutions per minute, the horsepower of the fan, or the fan motor horsepower, the static pressure created by the fan, and the airflow volume. All of these variables are related. And these affinity laws or fan laws show us how they're related to one another. I already alluded to this particular point. These laws and the calculations related to these laws are really common on certification exams. You don't have to be a fan engineer. I'm certainly not a fan engineer, but you do need to know how to use these formulas that we're going to be taking a look at, and these different laws that we're going to be talking about. And the laws that we're talking about are expressed in the form of different formulas. All right, let's go ahead and take a look at the fan laws and the related formulas. Pressure and volume of the air are related to the revolutions per minute of the fan impeller. The faster the impeller turns, the greater the pressure that's created and the greater the volume of air that's being moved by the fan. And these are the formulas representing this particular fan law. Or actually, these are two fan laws here that we're talking about, and these are the two formulas related to those fan laws. CFM, that's cubic feet of air moved per minute. RPM, that refers to the revolutions per minute that the impeller is turning. P refers to pressure, more specifically static pressure. RPM, again, revolutions per minute. In this particular formula, we have horsepower and RPMs. The RPMs of the fan related to the horsepower of the fan motor. Now, these are some equivalent formulas that you might run into. The formulas that I showed you on this page, these are the formulas that are used on the CSP exam. But as you study fan laws perhaps in more detail, you might run into some of these different variations of the formulas that we're talking about. Again, mathematically equivalent, but just laid out differently. And as I've already said, there are other fan laws, including fan laws related to the diameter of the impeller and the velocity of the impeller, which is different than RPMs of the impeller. But again, we're just focusing on the formulas, the laws that I've already shown you. We're not getting into diameter of the impeller or impeller velocity. And the main reason I'm not getting into it is because it's not a thing on the CSP exam. You don't have to worry about it on the CSP exam. Okay, here's the kind of problem you might see on the CSP exam. Rotational speed of a fan was changed from 1450 RPMs to 1750 RPMs to increase airflow. If the airflow at 1750 RPMs is 10,500 cubic feet per minute, what was the airflow at the fan speed of 1450 RPMs? This is the formula that we use. It's a representation of fan law 1, and it represents a relationship between the cubic feet per minute of air that's being moved at different RPMs. Now, everything we need to solve this problem is in the problem. We just need to plug in our numbers. Again, we have CFM2, 10,500. We have RPMs2, 1750. And we have the original RPMs of 1,450. Again, the question is asking us, what was the airflow when the fan was spinning at 1,450 revolutions per minute? Okay, once we have the numbers plugged in, mathematically, we're going to cross multiply. Now we want to get this unknown variable. This is the subject of this particular equation. That's what we want to solve for, is cubic feet per minute at time 1 when the RPMs were 1450. So to isolate CFM1, we cross multiply. We end up with CFM1 multiplied by 1750. Cross multiply these terms. Then we cross multiply these terms. 10,500 multiplied times 1,450. And we still don't have the subject variable isolated. We need to isolate that variable, and we will isolate that variable by dividing both sides by 1,750. When we divide this side by 1,750, it cancels on the left of the equal sign. When we divide the right side by 1,750, the term on the right side will take this form. Now all we need to do is the mathematical operations, and we will have the answer to this particular problem. When we multiply 10,500 by 1,450, we end up with 15,225,000. Divide that by 1750, we find that the cubic feet per minute moved by the fan at 1,450 RPMs was 8,700. 8,700 cubic feet per minute are being moved by the fan when the RPMs are at 1,450. Again, this is a common type of problem that you might see on a certification exam. Let's look at another example. Okay. Rotational speed of a fan was changed from 1,450 to 1,750 RPM. If the air pressure at 1,450 RPM is 6, what is the pressure at a fan speed of 1,750 RPMs? Now this one's a little bit different. Again, this is the formula that we use. We use the formula that states the relationship between pressure and RPMs. The formula looks different. It's a little bit different. The way we'll solve it's a little bit different. But it's still, the first step is getting your formula written down and plug in the values that you do have. We have the pressure at time 1 is 6. We have the RPMs at time 1, 1450. And we have the RPMs at time 2, which is 1750. And we're wanting to find out what our pressure created by the fan is going to be at an RPM level of 1,750 revolutions per minute. Okay. Once we get our numbers plugged in, then we need to isolate. Go back one step here. We need to isolate the subject variable. We're solving for the pressure at time 2. There's a couple of different ways you can do your transposition algebraically. I'm going to show you both methods, and you can use whichever method you like. My preferred method is to take the reciprocal of both sides of the equation. When you take the reciprocal, you are flipping things around. Notice the difference here. Instead of P sub 2 being on the bottom in the denominator position, it's now in the numerator position. Same thing on the right side of the equal sign. 1450 and 1750 have been flipped, so now we have 1750 over 1450. Okay, again, this is only one way, and if something's not clear on what I'm doing here algebraically, let me know. I'm going to show you the other method on the next slide. But again, this is my preferred method. You use whatever you do to one side of the equal sign, you can do to the other side. So I'm flipping things around on the left side, so I got to flip things around on the right side also. And when I do that, we end up with the problem looking like this, or the equation looking like this. When we are in this particular configuration, we can isolate pressure at time 2 by multiplying both sides times 6. When we multiply both sides of the equation by 6, it cancels on this side, and we end up with this. We have pressure at times 2 equals 6 times this term. And once we get to this point, it's just a matter of doing the math. First thing we want to do is divide 1750 by 1450. That's 1.21. Now we want to take the square of 1.21. That gives us 1.457. Now the very last thing we do is we multiply 6 times 1.457. Our pressure at time 2 is 8.74. The pressure increased from 6 to 8.74 with an increase in the fan speed from 1450 to 1750 RPMs. All right, like I said, that's just one method algebraically to solve this problem. Let me show you the other method. Again, same problem, but we're using a different method. Everything's the same. Plug in our values. Instead of using the reciprocal approach where we flip everything, we're going to take this term on the right and divide it by 1. Now, when we divide this term by 1, we haven't really done anything mathematically. Those are equivalent terms. 1450 divided by 1750 squared is equal to 1450 divided by 1750 squared over 1. So we haven't changed anything. But what we're doing, we're configuring the problem so now we can cross multiply. Once we have the formula set up in this configuration, we can cross multiply. And when we cross multiply, we end up with P sub 2. Go ahead and, okay, we're cross multiplying this term and this term, and then this term and this term. And we end up with pressure at time 2 multiplied by 1450 divided by 1750 squared. Then on the right side of the equation, we have 6 times 1. Divide both sides. Now, we still need to isolate pressure at time 2. To do that, we need to divide both sides by 1450 divided by 1750 squared. When we do that, it is canceled on the left side, and we end up with the equation looking like this, where we have pressure at time 2 equals 6 divided by 1450 divided by 1750 squared. We need to go ahead and do the calculations for this term. 1450 divided by 1750 is 0.829. We still need to square that. When we square 0.829, we end up with 0.687. Now the very last step in the calculation, we divide 6 by 0.687, and we find the exact same pressure that we found using the other method. Pressure at time 2 at 1750 RPMs is 8.74 inches of water, or water column. And we've talked about the units that are used for measuring pressure in class. All right, any questions about this, let me know. I know you can't ask questions right now in the middle of the video, but you could text me if you had a question. If you're watching the video, you're trying to work through the practice problems. Feel free to text me. All right, let's look at another problem. Rotational speed of a fan was changed from 1,000 RPMs to 1,500 RPMs. If 4 horsepower are required to produce 1,000 RPMs, what is the horsepower required to run the fan at 1,500 revolutions per minute? And here's the formula we use for this problem. This formula states the relationship between horsepower of the fan motor and RPMs of the fan. Just plug in the numbers and solve for the unknown. In this situation, our unknown is horsepower at time 2. We want to know what horsepower is required to generate 1,500 revolutions per minute. So we plug everything in. Our horsepower at time 1 is 4. Our RPMs at time 1 is 1,000. and then our RPMs at time 2 is 1500. And just like the previous problem, we're going to use the reciprocal method. We're going to flip everything this is the original. We flip it around and it takes this form. Horsepower at time 2 divided by 4 equals 1500 divided by 1000 cubed. Once we're at this point, we multiply both sides by 4. When we do that, the 4 is canceled on the left side, and we end up with this iteration. And once we get here, it's just a matter of doing the math. 1500 divided by 1000 is 1.5. We cube that, we end up with 3.375. Multiply 3.375 times 4. We find that we need 13.5 horsepower to turn the fan at 1500 revolutions per minute. And here is the alternative. This is using the cross multiplication method, but I'm actually taking a shortcut here. If you look at this and you don't understand it and you would like to understand it, let me know. But this is the cross multiplication method, but I just took liberties with my shortcuts. The short story here is you end up with the same solution, either method. All right, have any questions? Let me know. And this is our last problem. And this problem of all of these examples that we've looked at, this is the kind of problem you're most likely to see on a certification exam. It's multiple steps. It's a little more involved, and that's what the examination writers like to put on the CSP exam: multiple part problems. But let's go ahead and dive into it here. Then I'll show you how to solve it. You are currently running a 3 horsepower fan turning at 850 RPMs. The system is producing an air volume of 400 cubic feet per minute. What horsepower is required to produce an air volume of 500 cubic feet per minute? We want 500 cubic feet per minute out of this system. And at 3 horsepower, we get 400 cubic feet per minute. How many horsepower do we need to go to get 500 cubic feet per minute? Again, multiple step problem. We can't go from horsepower directly to air volume or from air volume directly to horsepower. We've got to first find the RPMs necessary to generate 500 cubic feet per minute of airflow. And here's the formula that expresses the relationship between cubic feet per minute and RPMs. We have everything we need in this form or in the problem to solve for the RPMs that we need. Then once we have the RPMs, then we'll use another formula to solve for the horsepower. But RPMs first. Plug everything in. CFM at time 1 is 400. CFM at time 2 is 500. Our RPMs at time 1 is 850. We want to find the RPMs that it's going to take to turn the fan at to generate 500 cubic feet per minute of airflow. Simple cross multiplication is all we need on this one. 500 times 850, then 400 times RPM at time 2. To isolate RPM at time 2, we need to divide both sides by 400. When we do this, the equation looks like this. We have 500 times 850 divided by 400. RPM is isolated on the right side of the equation. That's what we want. All we have to do now is some multiplication and some division. 500 times 850, 425,000. Divided by 400, 1,062.5 RPMs are required to generate 500 cubic feet per minute of airflow. Okay, to achieve a flow rate of 500 cubic feet per minute, the fan needs to turn at 1,062.5 RPMs. So we've got that part of the problem done, but we're looking for horsepower. So now that we've got the RPM solved, we can use that to solve for horsepower that we need to generate 500 cubic feet per minute of airflow. And using this formula, plug in our information. Our horsepower at time 1 is 3. Our RPMs at time 1, 850, and we just calculated the RPMs at time 2, 1062.5. Take the reciprocal of both sides, like we've done on previous problems. Isolate horsepower at times 2 by multiplying both sides times 3. When we do that, the 3 on the left side of the equation cancels out, and we end up with this configuration of our variables. Horsepower at times 2 equals 3 times this term. Go ahead and do the calculation inside the bracket. 1062.5 divided by 850, 1.25. Now we need to cube that. When we cube 1.25, it comes out to 1.95. Multiply the 1.95 times 3, and there's our horsepower. To achieve a flow rate of 500 cubic feet per minute, the fan needs to turn 1,062 RPM. To run the fan at 1,062 RPM, the fan motor needs to provide 5.85 horsepower. And that's the answer to this particular question, 5.85 horsepower. That gives us a pretty good introduction to the types of problems like these that you're likely to see on the CSP exam. Let me know if you have any questions. Also, let me remind you, if you would like to download these videos from Blackboard, you can do that. You'll just need a hard drive or a flash drive or something to download them to and keep them stored. I know for most of you it will be 3, 4, maybe 5 years before you're ready to take certification exams. So you can download the videos and have them stored for use at a later date. Let me know if you have any questions. I'll see you in the next video, and I'll see you in class.